What if everything you thought you knew about time was just the tip of the iceberg? Picture this. You're standing at the edge of a black hole, where the fabric of space-time twists like a ribbon in the wind. Here, seconds stretch into years, and the past, present, and future blur into something unrecognizable. This isn't science fiction. It's the bizarre reality predicted by Einstein's theory of relativity. And it raises a question that has haunted scientists and dreamers alike for centuries. Is time travel possible in our universe? The idea of journeying through time has captivated humanity for generations. From H.G. Wells' iconic time machine to blockbuster films like Back to the Future, we've long fantasized about bending time to our will. But strip away the Hollywood glamour, and you'll find something even more astonishing: real scientific theories that suggest time travel might not be as far-fetched as it seems. Think about it. If time can slow down near a black hole or speed up in the vast emptiness of space, who's to say we can't find a way to navigate its currents? The laws of physics, as we understand them, leave the door tantalizingly open. So let's embark on a journey together, one that will take us from the groundbreaking equations of Einstein to the mind-bending experiments in quantum mechanics. We'll separate fact from fiction, exploring how wormholes, cosmic strings, and even light itself could hold the keys to traversing time. Whether you're a skeptic or a believer, by the end of this exploration, you'll see the universe and time itself in a whole new light. The mysteries we're about to unravel aren't just about science. They're about the very nature of reality, and who knows, by the time we're done, you might just find yourself questioning whether time travel is already happening right here, right now. To understand whether time travel could ever be possible, we first need to unravel one of the universe's greatest mysteries: what time actually is. Think of space-time as a vast, cosmic tapestry where space and time are woven together. While we can move freely through space, walking forward, backward, or sideways, time seems to march relentlessly in one direction, forward. But why? The answer lies in something called entropy, a fundamental principle of thermodynamics that measures disorder in the universe. Picture a shattered glass. Once broken, it never spontaneously reassembles itself. That's entropy at work, driving time's arrow in a single, irreversible direction. Now here's where things get fascinating. The laws of physics as we know them don't actually forbid time from running backward. Einstein's equations treat time as just another dimension, mathematically no different from space. In theory, there's nothing stopping time from flowing in reverse except for entropy. Every time you stir cream into coffee or blow out a candle, you're witnessing entropy increase, locking time into its forward march. But what if we could find a way to reverse entropy or sidestep it entirely? Some physicists speculate that wormholes, hypothetical tunnels through space-time, might offer a shortcut, bending time into a loop where past and future connect. And then there's causality, the idea that causes must always come before effects. Drop a ball, and it hits the ground, never the other way around. This unbreakable rule keeps our universe logical and predictable. But in the bizarre realm of quantum mechanics, particles sometimes seem to defy causality, behaving in ways that hint at a more flexible relationship with time. Could these quantum quirks hold the key to manipulating time on a larger scale? The deeper we dig, the clearer it becomes. Time isn't just a ticking clock. It's a dynamic, malleable force woven into the very structure of reality, and if we can learn to navigate its currents, the possibilities could be limitless. Einstein turned our understanding of time upside down when he revealed that clocks don't tick at the same rate for everyone. Imagine two identical watches, one placed on a mountain, the other at sea level. After a year, the higher clock runs slightly faster because gravity's grip weakens with altitude. This isn't a thought experiment. It's been confirmed by ultra-precise atomic clocks. But the real game changer comes when we push this idea to the extreme. Picture a spaceship racing near light speed. For the astronauts on board, time would crawl compared to those on Earth. A few hours for them could mean decades back home, a one-way trip to the future built into the fabric of reality. Now, take this further to the most extreme environment in the universe, a black hole. Near its event horizon, where gravity warps space-time like a whirlpool, time stretches to a near standstill from an outsider's perspective. If you could skim the edge of a black hole and return, something theoretically possible, if not exactly survivable, you might find Earth civilization has advanced centuries while you aged mere days. This is time dilation cranked to its limits, a natural time machine powered by gravity itself. But relativity offers another tantalizing possibility: closed time-like curves. These are paths through space-time that loop back on themselves like a cosmic Möbius strip. In theory, if you could create or find such a curve, perhaps within a rotating universe or around an infinitely long cosmic string, you might travel to your own past. The equations allow it, but the universe seems to fight back with paradoxes. Step on a butterfly in the past, and could you erase your own future? Physics has ways to potentially resolve these headaches, like the self-consistency principle, which suggests the universe would conspire to prevent contradictions. Yet for all its elegance, relativity alone doesn't make time travel easy. The energies required to bend space-time that drastically are beyond anything we can harness for now. But the mere fact that the math doesn't forbid it has kept the dream alive. From GPS satellites that adjust for time dilation to pulsars whose spins confirm relativity's predictions, we're already living in a world where time is fluid. The next step, learning to steer its flow. Wormholes might sound like pure science fiction, but they emerge straight from the equations of general relativity as cosmic shortcuts threading through space-time. Picture the universe as a vast sheet of paper, folded so two distant points nearly touch. A wormhole would be like poking a pencil through that fold, creating a tunnel that bypasses the long journey across the surface. In theory, stepping into one end could let you emerge light years away, or even in another time. The math checks out, but here's the catch. These tunnels would snap shut instantly unless held open by something truly bizarre. That's where exotic matter comes in, a hypothetical substance with negative energy that could prop a wormhole open like cosmic scaffolding. Unlike anything we've found in nature, this matter would defy gravity, pushing space-time outward to keep the tunnel stable. But even if we could somehow create or find such a substance, the challenges don't end there. Quantum effects near a wormhole's throat might trigger a lethal feedback loop of radiation, vaporizing anything daring enough to enter. It's like trying to walk across a bridge made of soap bubbles. One wrong step, and the entire structure pops. Yet the most tantalizing possibility isn't just crossing space, it's leaping through time. If one end of a wormhole accelerated near light speed or hovered near a black hole's edge, time would slow down there relative to the other end, return to the stationary side, and you might find yourself decades in the past or future. But this raises a dizzying paradox. What if you traveled back and prevented the wormhole's creation in the first place? Some physicists argue that quantum mechanics might enforce a kind of cosmic censorship, tweaking events to avoid contradictions. Others suggest wormholes could only connect to times after their own formation, sidestepping the paradox altogether. The truth is, wormholes remain a dazzling what-if at the edge of known physics. While we've yet to spot one or even confirm exotic matter exists, their theoretical allure keeps scientists probing. After all, black holes were once considered mathematical oddities until we photographed one. Could wormholes be hiding in plain sight, warping space-time in ways we're only beginning to imagine? For now, they remind us that the universe's greatest mysteries often start as scribbles on a chalkboard waiting for the bold to test them against reality. The grandfather paradox is one of those mind-bending puzzles that makes time travel seem impossible until you peel back the layers. Imagine going back in time and accidentally preventing your grandparents from meeting. No grandparents, no parents, no you, so how could you have traveled back in the first place? It's a logical knot that feels unsolvable, but physicists have proposed some fascinating ways the universe might untangle it. One compelling idea is the self-consistency principle, which suggests reality has a built-in safety net. No matter what you try to change in the past, the universe would conspire to keep events consistent. Maybe your attempt to interfere would fail. A gun jams, a missed train, a sudden change of heart. Like a cosmic editor, the timeline might subtly correct itself to preserve causality. This isn't just speculation, it's rooted in the math of closed time-like curves, where any action taken in the past would already be part of history. You couldn't alter what's already happened because, in a way, you always played your part. Then there's the multiverse approach. Instead of a single, unchangeable timeline, every decision could spawn a new, parallel universe. Step back in time to stop your grandparents' meeting, and you'd simply branch off into a reality where they never did, while the original timeline carries on untouched. This sidesteps the paradox entirely, but it raises another question. If you're no longer in your own universe, have you really traveled through time, or just slipped sideways into another version of reality? Quantum mechanics adds another twist. At the subatomic level, particles behave in ways that defy classical logic, existing in multiple states until observed. Some physicists suggest time might work similarly, existing not as a single thread but as a web of possibilities. In this view, paradoxes might just be artifacts of our limited perception, like a two-dimensional creature trying to grasp the concept of depth. So could time travel ever be free of paradoxes? The answer might depend on how deeply we're willing to redefine reality. Whether through self-correcting timelines, branching universes, or quantum weirdness, the universe seems to have ways of keeping time's story coherent. And that's the real puzzle, not just whether we can twist time, but whether time itself is far stranger than we've ever imagined. If particles can exist in two places at once or communicate instantaneously across vast distances, why not across time? Quantum mechanics shatters our everyday notions of reality, and its strangest phenomena might rewrite the rules of time itself. Take quantum entanglement, where two particles become mysteriously linked, change one, and its partner responds instantly, no matter how far apart they are. Einstein called this spooky action at a distance, but what if that spookiness isn't just about space? Some experiments suggest entangled particles might even influence each other's past states, as if quantum connections can reach backward through time. Then there's superposition, the mind-bending idea that particles exist in multiple states until observed. A single electron isn't just here or there, it's both, hovering in a haze of possibilities. Apply this to time and you get the quantum time flip, where an event might not have a fixed past or future until it's measured. Think of Schrödinger's famous cat, both alive and dead in its box. Now imagine that box exists across decades. Could the cat's fate ripple backward, rewriting its own history? The many worlds interpretation takes this further, proposing that every quantum decision spawns a branching universe. Miss a train in one timeline, there's another where you caught it, and another where the train never existed. If time is a tree with infinite branches, could we hop between them? Some theorists speculate that quantum tunneling, where particles suddenly bypass barriers, might allow brief leaps across timelines, like skipping stones between parallel realities. But here's the kicker: quantum effects usually vanish at larger scales. A single electron might defy time, but could trillions of them conspire to send a person through the ages? The answer might lie in harnessing quantum coherence, keeping particles synchronized long enough to amplify their weirdness. Recent experiments with tiny time crystals, structures that repeat in time like diamonds repeat in space, hint that temporal control could be more than fantasy. Of course, the universe seems determined to guard its secrets. Quantum decoherence scrambles delicate superpositions, and entropy still pushes time forward. Yet the mere possibility that time's arrow might wobble at the quantum level keeps physicists awake at night, because if we can't break time's rules, perhaps we can bend them just enough to peek beyond the veil. Black holes aren't just cosmic vacuum cleaners, they're nature's most extreme time machines. Picture this: you're circling a black hole in a spacecraft, skimming just outside its event horizon where gravity twists space-time into a knot. For every hour you spend there, decades could pass on Earth. This isn't hypothetical, it's the brutal reality of Einstein's general relativity. The closer you get to a black hole's immense gravity, the more time slows down for you relative to the outside universe. It's like stepping into a sci-fi movie, except the science is real. But let's break down why this happens. Space-time isn't just a stage for the universe, it's a dynamic fabric that bends and stretches under mass. A black hole, with its unimaginable density, warps this fabric so intensely that time itself drags to a crawl near its edge. Think of it like walking through syrup. The deeper you go, the harder it is to move forward. For an astronaut orbiting the black hole, time would appear normal, but anyone watching from afar would see their movement slow to a glacial pace. This effect, called gravitational time dilation, has been measured right here on Earth. Clocks on GPS satellites tick slightly faster than those on the ground because they're farther from Earth's gravity. Now amplify that by 1 billion and you've got a black hole's time warping power. The catch: surviving the trip. Even if you could resist the pull of the event horizon, the tidal forces near a black hole would stretch you like taffy. Gravity's grip is so uneven that your feet would feel exponentially stronger pull than your head, a phenomenon colorfully called spaghettification. Then there's the radiation. As matter spirals into a black hole, it heats up to millions of degrees, creating a swirling disk of supercharged particles that blast out lethal X-rays. Your ship would need more than heat shielding, it'd need a miracle. But suppose you could overcome these hurdles. What would time travel via black hole actually look like? Let's say you orbit for 5 years near the event horizon and then return to Earth. Depending on the black hole's size and your orbit's proximity, you might find Earth's civilization has advanced centuries or even millennia. You wouldn't just be a time traveler, you'd be a relic from another age. And here's the twist: there's no going back. While black holes might fling you into the future, reversing the journey would require bending space-time in ways even they can't manage. The strangest part: black holes might not just distort time, they could fracture it. Some theories suggest that deep inside a black hole, space-time curves so violently that the concepts of before and after lose meaning. It's like reaching the edge of a map where the rules of navigation no longer apply. Could there be regions where time loops back on itself, creating natural time tunnels? The math allows for it, but the universe seems determined to keep those doors locked behind walls of fire and chaos. Yet for all their dangers, black holes offer something extraordinary: proof that time is fluid. They're cosmic laboratories where the universe tests the limits of reality itself. And while we may never ride one into the past, their very existence whispers a tantalizing promise. that time, for all its apparent rigidity, might just be the universe's most flexible illusion. Cosmic strings sound like something straight out of mythology, threads of pure energy thinner than an atom but stretching across the entire universe. Yet these bizarre relics of the Big Bang aren't just theoretical curiosities. They might be the ultimate cosmic sewing needles, stitching together the fabric of space-time itself. Picture the universe just moments after its birth, a seething cauldron of unimaginable energy. As it expanded and cooled, cracks might have formed in the very structure of reality, like flaws in a frozen lake. These cracks, cosmic strings, would carry the weight of entire galaxies in their gravitational wake, warping space-time around them with such intensity that time itself could twist into knots. Now imagine two of these strings racing past each other at nearly the speed of light. According to physicist J. Richard Gott, this cosmic dance could create something extraordinary, a closed time-like curve, a loop in space-time where the end of your journey might deposit you right back at the beginning. It's like drawing a circle on a piece of paper, then folding the paper until the pencil line touches itself suddenly. The path has no start or finish. The math suggests that under these extreme conditions, time could coil into a helix, allowing you to walk your own timeline like a spiral staircase. But here's the catch: cosmic strings, if they exist at all, would be nearly impossible to detect. Without mass as we know it, they wouldn't absorb or emit light, only their gravitational fingerprints might betray them. Astronomers have searched for their signatures in the subtle warping of distant starlight or the faint ripples in the cosmic microwave background, but so far, no smoking gun. And even if we found one, harnessing its power would require engineering on a scale that dwarfs human capability. You'd need to move these cosmic threads at relativistic speeds, a task akin to pushing a freight train with a feather. Yet the mere possibility raises profound questions. If time loops could form naturally in the universe, does that mean the past, present, and future are more fluid than we think? Could the universe contain hidden corridors where history folds back on itself, like a Möbius strip of causality? Some theorists speculate that quantum fluctuations near cosmic strings might spawn baby universes, branching realities where time flows in entirely new directions. Others warn that even approaching a string could unleash catastrophic gravitational waves, shredding matter into subatomic confetti. The truth is, cosmic strings occupy the razor's edge between physics and philosophy. They remind us that the universe's infancy might have left behind artifacts stranger than fiction, and that time, for all its apparent rigidity, might still carry the faint echoes of its molten origins. Whether they're the keys to time travel or just cosmic mirages, one thing's certain: the deeper we probe the universe's scars, the more we realize how little we truly understand about the nature of time itself. Time crystals sound like something ripped from the pages of a science fiction novel, structures that pulse and repeat not in space but in time itself. Unlike ordinary crystals where atoms arrange in predictable spatial patterns like diamonds or snowflakes, time crystals break the mold by cycling through states in a never-ending loop, even without any energy input. Picture a clock that ticks forever without being wound, or a pendulum that swings perpetually without any push. This bizarre behavior was once thought impossible, until Nobel laureate Frank Wilczek proposed their existence in 2012, and researchers actually created them in labs just 5 years later using chains of ions or defects in diamonds. What makes these crystals so revolutionary is how they defy our everyday intuition about motion. Normally, systems settle into equilibrium. Think of a cup of coffee cooling to room temperature. But time crystals never settle. They're like a dance that never stops, where the dancers keep moving even after the music fades. This happens because their quantum states become locked into a rhythm, flipping back and forth between configurations with a regularity that's eerily precise. It's as if time itself becomes part of their structure, woven into their very existence. Now, here's where things get wild. If we could scale up these tiny, lab-grown curiosities, could they manipulate time on a larger scale? Some theorists speculate that arrays of time crystals might act like quantum metronomes, synchronizing events across different points in spacetime. Imagine a network of these crystals creating a kind of time lattice, where disturbances in one part ripple backward or forward, effectively nudging causality out of its usual straight line. While this wouldn't let you hop into a time machine a la H.G. Wells, it might allow for delicate control over the sequence of events, like sending a signal into the past or holding a quantum state stable across time. But before we get ahead of ourselves, there's a catch. Time crystals don't violate the second law of thermodynamics. They can't pump energy into the universe or create perpetual motion machines. Their motion is more like a phantom echo, a shadow play of quantum coherence, and scaling them up to macroscopic sizes, that's a hurdle we're nowhere near overcoming. The delicate quantum states that give time crystals their properties are easily destroyed by noise and interference. A single stray photon could unravel the entire system. Yet their very existence forces us to rethink the nature of time. If matter can be engineered to remember its motion indefinitely, does that mean time isn't just a backdrop but an active participant in the universe's structure? Could these crystals be glimpses of a deeper symmetry in physics, one where time and space are even more deeply entwined than relativity suggests? For now, time crystals remain a tantalizing laboratory curiosity, but they've already cracked open a door to possibilities we're only beginning to explore. And in that uncertainty lies the thrill, because sometimes the most profound revolutions start with a single, impossible tick of a quantum clock. Dark matter and dark energy are the universe's greatest enigmas, invisible, undetectable, yet making up 95% of everything that exists. We're like sailors adrift in an ocean, aware only of the 5% floating above the surface, while the vast depths below remain shrouded in mystery. But what if these unseen forces hold the key to manipulating time itself? Dark matter's gravitational grip bends light and distorts galaxies, acting as the universe's hidden scaffolding. Could its invisible fingers also twist spacetime into pathways that bypass the present? Meanwhile, dark energy pushes the cosmos apart at an accelerating rate, stretching the very fabric of reality. If we could tap into these forces, might we find a way to stretch time like taffy, or snap it back like a rubber band? Take dark matter first. Unlike ordinary matter, it doesn't emit, absorb, or reflect light, yet its gravitational influence is undeniable. Galaxies rotate so fast they should fling themselves apart, unless an unseen mass holds them together. This cosmic glue warps spacetime just like visible matter, but with a crucial difference: it doesn't interact with electromagnetic forces. That means dark matter could, in theory, form dense filaments or exotic structures that bend time in ways ordinary matter can't. Imagine a river where the current flows differently beneath the surface. Dark matter might create similar hidden eddies in time, invisible to us but potentially navigable. Some models even suggest that concentrated dark matter could generate closed time-like curves, those elusive loops where time folds back on itself. Then there's dark energy, the even more perplexing force driving the universe's accelerated expansion. Think of it as anti-gravity pushing galaxies apart faster and faster. If dark energy can stretch space itself, could it also stretch time? One radical idea proposes that regions of intense dark energy might create time bubbles, where clocks tick at wildly different rates compared to the outside world. It's like stepping into a pocket of the universe where time operates by its own rules, a cosmic loophole in the flow of causality. But here's the catch: we don't even know what dark energy is. Is it a property of space itself, as Einstein's cosmological constant suggested? Or is it a dynamic field, like an invisible ocean with currents that could someday reverse? The answers might rewrite our understanding of time's arrow. If dark energy's push can accelerate, could it also decelerate or even pull space-time backward? The math allows for it, though the universe seems to guard such possibilities fiercely. The tantalizing thread connecting these ideas is scale. Dark matter and energy operate across cosmic distances, their effects subtle over human lifetimes but profound across eons. To harness them for time travel, we'd need to concentrate their influence locally, like bottling a hurricane. Some theorists speculate that primordial black holes, those elusive remnants of the Big Bang, might be knots of dark matter dense enough to warp time meaningfully. Others imagine futuristic technologies that could mimic dark energy's repulsive force, creating artificial time fields. But for now, these remain dreams scribbled at the edge of known physics. Yet the very existence of these mysteries hints at something extraordinary. The universe is far stranger than we've dared to imagine. If 95% of reality is invisible and unexplained, who's to say time travel isn't hiding in that shadowy expanse? Every breakthrough in understanding dark matter and energy peels back another layer of the cosmic onion, and with each layer, the rules of time seem a little less fixed, a little more ripe for rewriting. Hollywood has given us some unforgettable time travel stories: DeLoreans hitting 88 miles per hour, astronauts slipping through wormholes near Saturn, even entire cities vanishing into alternate timelines. But while these tales thrill us, they often play fast and loose with physics. Take Back to the Future's iconic flux capacitor. The idea of a car generating enough energy to fracture time is pure fantasy, even if we ignore the fact that accelerating to time warping speeds in a mall parking lot would require more energy than the entire planet produces in a year. Yet buried beneath the spectacle, there's a kernel of truth. Einstein's relativity does link speed and time, just not in a way Marty McFly would recognize. Compare that to Interstellar, where Matthew McConaughey's crew orbits a supermassive black hole named Gargantua. Here, the science gets eerily accurate. The film's depiction of time dilation, where hours on the water planet equal years back on the ship, mirrors real physics. Near a black hole's immense gravity, clocks do tick slower relative to the outside universe. Even the swirling accretion disk and lens flare effects were painstakingly modeled using equations from Nobel-winning physicist Kip Thorne. But the movie takes one creative leap, surviving the black hole's interior. In reality, the tidal forces would shred anything crossing the event horizon long before it reached a tesseract-like library of past moments. Then there's Primer, a cult classic that treats time travel like a math problem. Its low-budget time machine isn't flashy, just a box that slowly acclimates occupants to a reversed timeline. The film's dizzying loops and paradoxes edge closer to theoretical physics than most blockbusters, especially its portrayal of causality's fragility. Mess with the past and the consequences ripple unpredictably, a theme quantum physicists take seriously, but even Primer glosses over the energy requirements. Creating a closed time-like curve, as the characters do, would demand densities of matter we've only theorized, like the aforementioned cosmic strings. So why the gap between fiction and reality? Filmmakers prioritize drama over equations, and rightly so. Watching someone calculate Lorentz transformations for 2 hours wouldn't exactly pack theaters. But the best sci-fi uses real science as a springboard, stretching it just enough to ignite wonder without snapping our suspension of disbelief. Arrival's linguistic time play, for instance, borrows from the Sapir-Whorf hypothesis, while Tenet's inverted entropy nods to thermodynamics' arrow of time. These stories succeed because they root the extraordinary in the possible, letting us taste the universe's strangeness without choking on the math, the takeaway. Time travel in pop culture is less about accuracy and more about asking what if, the same question that drives real scientific breakthroughs. Whether it's a phone booth or a wormhole, these stories remind us that the universe's rules are wilder than we imagine. And sometimes the line between science and fiction is thinner than a single, twisted timeline. The idea of scientists tinkering with time might sound like the plot of a summer blockbuster, but the truth is stranger than fiction. Take the Large Hadron Collider, the most powerful particle accelerator ever built. While its primary goal is to smash protons together at near light speed to uncover the universe's fundamental building blocks, some theorists speculated it could inadvertently create microscopic time loops. How, at those unimaginable energies, space-time itself might ripple like a pond, forming fleeting wormholes or even particles that briefly travel backward in time. In 2008, researchers even debated whether the LHC's collisions could produce Higgs singlets, hypothetical particles that might slip between dimensions and perhaps even moments in time. Though no evidence has emerged, the fact that physicists seriously considered the possibility shows how deeply time's flexibility is woven into our equations. Then there's quantum teleportation, a real phenomenon that sounds ripped from science fiction. Scientists have successfully transmitted quantum states between particles instantaneously across distances exceeding 1,000 kilometers, exploiting the spooky link of entanglement. But here's the twist. Some interpretations suggest these entangled particles might not just defy space, they could blur time's arrow. In 2013, an experiment at the University of Queensland showed that measuring a photon's quantum state could retroactively alter its entangled partner's past behavior. It's as if the present reached backward to tweak history, a phenomenon dubbed retrocausality. While this doesn't mean we're sending messages to the past, it hints that time at the quantum level might not be the rigid, one-way street we experience. Perhaps the most controversial claim comes from experiments with closed time-like curves in the lab. In 2017, a team at the University of Queensland simulated how a quantum particle might behave if it looped back in time to interact with its past self. The results: the particle's actions became paradox-proof, aligning with the self-consistency principle like a cosmic editor, ensuring the timeline stays coherent. Critics argue this is just a mathematical trick, a clever simulation with no real-time travel. But supporters counter that if quantum systems can model time loops without breaking causality, who's to say nature doesn't exploit this trick on scales we've yet to detect? Even NASA has dipped its toes into temporal experimentation. Their White Jude warp field interferometer aims to detect microscopic distortions in spacetime that could, in theory, lead to warp drive technology, an idea inspired by physicist Miguel Alcubierre's proposal to compress space ahead of a ship and expand it behind, effectively surfing a wave of spacetime. While this focuses on faster-than-light travel, the same principles might one day apply to time manipulation. After all, relativity tells us speed and time are two sides of the same coin. Yet for all these tantalizing hints, the sobering reality is that no experiment has definitively cracked time travel. The effects observed are fleeting, microscopic, and often hotly debated. But the mere fact that serious researchers are probing these questions, funded by institutions like CERN and NASA, speaks volumes. Time travel isn't just the stuff of fantasy. It's a frontier of science, explored not with DeLoreans but with particle accelerators and quantum circuits. And who knows, the next big breakthrough might not come from a flashy machine, but from a quiet lab where someone notices time behaving in a way no one expected. What if every attempt to change the past was doomed to fail, not by chance, but by the universe's ruthless enforcement of its own rules? That's the spine-chilling premise of the Novikov self-consistency principle, a theory that reshapes how we think about time travel's consequences. Proposed by Russian physicist Igor Novikov in the 1980s, this idea suggests that the universe operates like a meticulous editor, snipping away any contradictions before they can unravel causality. Picture this: you travel back to prevent a historical disaster, only to find your actions inadvertently cause the very event you tried to stop. The bullets you dodged, the warnings you gave, all of them were always part of the timeline, stitching history together with invisible threads. This principle elegantly sidesteps the messy paradoxes that plague other time travel theories. Take the grandfather paradox, where killing your own ancestor would erase your existence. Novikov's universe wouldn't allow it. Maybe your gun jams or your grandfather ducks at the last second. The details don't matter. What matters is that reality bends to ensure the timeline remains coherent. It's like trying to write a sentence that contradicts itself. The universe simply backspaces until the story makes sense again. Even your free will becomes an illusion, constrained by the unbreakable tapestry of what's already happened. But here's where things get philosophically thorny. If our choices are prewritten by the past's inevitability, does human agency even exist in this model? Some physicists argue that Novikov's principle doesn't eliminate free will, it just redefines it. Your decision to time travel and intervene was always part of history, meaning your will and the universe's consistency coexist. Think of it like an actor improvising in a play where the script magically adapts to their choices. The audience sees a seamless story, but the performer still feels the thrill of spontaneity. The implications ripple beyond theory. If self-consistency governs time travel, then the future might be just as fixed as the past. Any attempt to alter tomorrow could be futile, as the universe steers events toward their correct outcomes. This aligns eerily with certain interpretations of quantum mechanics, where particles seem to know their future states in advance. Could time be less a river flowing in one direction and more a sculpted block, where every moment is already carved in stone? Yet for all its neat solutions, the Novikov principle raises as many questions as it answers. Why would the universe bother preserving consistency? Is there some deeper law, some cosmic preference for order over chaos? And what about branching timelines? Could self-consistency apply only to certain threads of reality? These aren't just thought experiments, they're cracks in the foundation of how we perceive cause and effect. Whether Novikov's vision holds up or not, one thing's certain: time, if it can be traversed, plays by rules far stranger than we've dared to imagine. What if every choice you've ever made spawned an entirely new universe? The concept of parallel realities isn't just wild speculation. It's a serious scientific hypothesis that could redefine our understanding of time travel. Imagine flipping a coin. In our world, it lands heads up, but according to the Multiverse Theory, another version of you just watched it land tails, in a separate, equally real universe. This dizzying idea, known as the many worlds interpretation, suggests that every quantum decision splinters reality into infinite branches. For time travelers, this could be the ultimate loophole. Step back in time to change history, and instead of creating a paradox, you'd simply spin off into a fresh timeline where the old rules no longer apply. The math behind this is rooted in quantum mechanics, where particles exist in multiple states until observed. Extend that to the cosmic scale, and you get a tapestry of universes, some where dinosaurs never went extinct, others where your childhood home had a different color door. Physicist Hugh Everett first proposed this in the 1950s as a way to resolve quantum ambiguities, but it soon became a playground for time travel theorists. If you killed your own grandfather in the past, the many worlds model says you wouldn't vanish, you'd just find yourself in a new branch where your original timeline remains untouched. Paradox solved, at least on paper, but here's the catch. If branching timelines are real, how would a time traveler ever return to their home universe? Every action would spawn another divergence, leaving them lost in an ever-expanding maze of realities. Some theories suggest wormholes or quantum entanglement might act as anchors, tethering travelers to their point of origin. Others argue that the very act of time travel could create a dominant timeline, where certain events remain fixed across most branches like cosmic guardrails preventing total chaos. Then there's the question of evidence. If infinite universes exist, why haven't we detected even a whisper of them? Some researchers point to mysterious cold spots in the cosmic microwave background, regions of space inexplicably cooler than their surroundings as possible bruises from collisions with other universes. Others hunt for gravitational anomalies that might reveal parallel worlds tugging on our own. So far, the data is tantalizing but inconclusive, leaving the multiverse hovering at the edge of accepted science. Critics argue that the many worlds interpretation is less a theory than a philosophical shrug, an elegant way to dodge hard questions about causality. After all, if every possible outcome happens somewhere, the idea of reality starts to feel meaningless. Why care about consequences if there's always a universe where things worked out? Proponents counter that the multiverse doesn't erase responsibility. It simply acknowledges the staggering complexity of existence. Your choices still matter, they're just not the only version of you making them. Whether the multiverse is science's next great frontier or a dead end, one thing's certain: it forces us to confront the fragility of our place in the cosmos. If time travel ever becomes possible, we might not just be navigating history, we'd be surfing an infinite ocean of alternate nows, each ripple a new reality waiting to unfold. And that raises the most haunting question of all. In a universe of endless possibilities, how do we know which one is truly ours? Right now, astronauts orbiting Earth on the International Space Station are aging slower than the rest of us, but only by milliseconds. This isn't science fiction. It's the unavoidable consequence of time dilation, where gravity and velocity warp the flow of time itself. The ISS hurtles around Earth at nearly 17,500 miles per hour, fast enough for relativity's subtle effects to kick in. Over a 6-month mission, astronauts actually return home about 0.007 seconds younger than if they'd stayed on the ground. It's a tiny difference, but it proves Einstein was right. Time isn't absolute. It bends, stretches, and twists depending on how fast you're moving and how strong gravity's grip is where you're standing. Now imagine cranking that effect up to extremes. What if we built spacecraft capable of traveling a significant fraction of light speed? At 90% the speed of light, time for the crew would slow to less than half the rate experienced on Earth. A 10-year journey for them could mean over 20 years pass back home. Push closer to light speed, say 99.9%, and the numbers get staggering. 1 year on board might equal 22 years on Earth. Suddenly, a trip to a nearby star wouldn't just cross space, it would vault travelers centuries into humanity's future. But here's the catch: reaching those speeds demands energy beyond anything we can currently produce. Accelerating even a small ship to 90% light speed would require more fuel than exists on Earth. The most plausible solution: a breakthrough like nuclear pulse propulsion, which could theoretically harness controlled atomic explosions, or antimatter engines, where matter-antimatter annihilations unleash pure energy. Even then, the engineering hurdles are mind-boggling. At such velocities, a collision with a grain of sand would release the energy of a nuclear bomb, forcing ships to carry shields strong enough to weather microscopic cosmic shrapnel. Then there's the human cost. Extended time dilation means astronauts might return to a world where everyone they knew has aged decades or died. Imagine leaving Earth in 2050, only to return in 2200 to a civilization that's moved on without you. Would explorers be willing to pay that price? Some scientists argue this very dilemma could explain why we've never encountered advanced alien civilizations. Perhaps they've all retreated into relativistic isolation, their timelines stretched thin by the demands of interstellar travel. Yet amidst these challenges, hope flickers in unexpected places. Time dilation's harsh math also offers a strange gift. It makes galactic exploration biologically possible. Without relativity's clock-slowing effect, a trip to the Milky Way's center would take 30,000 years, far beyond a human lifespan. But for a crew traveling at 99.999% light speed, the journey could feel like just a decade. They'd never see Earth again, but they could reach the stars within their lifetime. The irony, while we dream of bending time to explore the cosmos, we're already doing it every time we launch a satellite. GPS systems account for time dilation to keep your phone's maps accurate, proving that even the tiniest relativistic effects can't be ignored. So while we may not be leaping centuries forward anytime soon, we're already dancing with time's flexibility, and each small step brings us closer to mastering its rhythm. Stephen Hawking once joked that the absence of tourists from the future might be the strongest evidence time travel is impossible. But he wasn't just making a punchline, he was hinting at something far deeper. His chronology protection conjecture suggests the universe has built-in safeguards, like cosmic immune systems, that prevent paradoxes by making time travel to the past fundamentally impossible. Picture a river with an unseen current constantly pulling you forward. No matter how hard you swim backward, nature finds a way to keep you drifting downstream. Hawking's idea hinges on a peculiar quirk of quantum mechanics combined with general relativity. At the smallest scales, empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. When you try to warp space-time enough to create a time loop, say, by building a wormhole, these quantum fluctuations could theoretically amplify into an unstoppable feedback loop of energy. The result, a catastrophic surge that would destroy the time machine before it could be used, like a circuit overloading to prevent a short. Hawking called this quantum back reaction, nature's way of snipping paradoxes in the bud. But not everyone's convinced. Some physicists argue the conjecture is less a law and more a cosmic placeholder, a way to explain why we haven't seen time travelers rather than proving they can't exist. After all, black holes were once thought to violate physics until we observed them. Could chronology protection be similarly overturned? One counterpoint comes from quantum field theory, where certain solutions allow for self-healing timelines that absorb inconsistencies without collapsing. Think of it like a tree growing around a fence. The anomaly remains, but the timeline adjusts to accommodate it. Then there's the observational problem. If time travel to the past were impossible, why do the equations of general relativity permit solutions like closed time-like curves? Einstein's math openly allows for time loops, yet Hawking's conjecture insists reality rejects them. It's like discovering a door in your house that's welded shut. Why build the door at all? Some theorists propose a middle ground. Maybe time travel is possible, but only in contexts so extreme or isolated that paradoxes can't propagate. A black hole's singularity might churn with time loops, but they'd be trapped behind an event horizon, forever cut off from influencing the wider universe. The debate boils down to whether physics is prescriptive or descriptive. Does the universe actively police causality, or are we simply misunderstanding the rules? Hawking's conjecture leans toward the former, painting time as a guarded frontier. Yet the more we learn about quantum weirdness, entanglement's disregard for distance, retrocausality's blurring of before and after, the more chronology protection feels like a provisional fence, not an iron law. Perhaps time isn't something to be protected, but a landscape we're only beginning to map, full of terrain that seems impassable until we find the right path. For now, the conjecture stands as both a challenge and an invitation, proof that even our greatest minds couldn't untangle time's knots, but that the attempt itself reshapes what we think is possible. Whether it's proven or discarded, one thing's certain: the universe's secrets rarely yield to simple answers. Quantum entanglement is often called spooky action at a distance. For a reason, two particles can become so deeply linked that changing one instantly affects its partner, no matter how far apart they are. But what if this bizarre connection isn't just bridging space but time itself? Recent experiments have revealed something even stranger. Entangled particles might not just defy distance, they could be bending the arrow of time. Imagine flipping a coin in New York, and the moment it lands heads up, a coin in Tokyo instantly lands tails up. Now replace those coins with subatomic particles, and replace Tokyo with yesterday. That's the mind-bending possibility some physicists are exploring. Take the groundbreaking work of scientists at the University of Washington in 2018. They set up an experiment where a pair of entangled photons were measured in a specific order, except the order itself was randomized after the photons had already been detected. Astonishingly, the particles seemed to know how they'd be measured in the future, adjusting their behavior retroactively. It's as if the photons were peeking through time's keyhole, responding to choices that hadn't technically happened yet. This phenomenon, called retrocausality, suggests that quantum effects might ripple backward through time, rewriting the rules of cause and effect. But before we picture sending messages to the past, there's a catch. These time-defying tricks only work because quantum particles exist in a haze of probabilities until observed. Once measured, their states snap into place, and any retroactive influence becomes locked in the past. It's less like a time machine and more like a cosmic game of dominoes, where knocking over the last tile somehow makes the first tile fall. The universe, it seems, is fine with a little temporal flexibility at the quantum scale, as long as the final ledger balances. The real shocker: this might not be limited to lab experiments. Some theorists propose that quantum entanglement's time-bending properties could explain why the universe appears so finely tuned for life. If particles can subtly nudge their own past states, perhaps reality itself is the result of a vast, self-correcting loop, where the future gently molds the past to ensure its own existence. It's a dizzying thought that every atom in your body might be here today because, in some sense, the universe knew you were coming. Of course, not everyone's convinced. Skeptics argue that retrocausality is just a quirk of interpretation, a way to make the math tidy without any real-time travel happening. After all, if you can't send a deliberate signal to the past, can you truly call it time travel? Others counter that dismissing these effects is like ignoring the first flickers of fire because we don't yet have a steam engine. The quantum realm operates by rules we're only beginning to grasp, and what looks like a glitch today might be the foundation of tomorrow's breakthroughs. One thing's certain: if entanglement really does thread the needle of time, it hints at a universe far more interconnected than we ever imagined. not just across space, but across moments, a cosmos where past, present, and future might be woven together in ways we're only starting to untangle. And that raises a question even wilder than time travel. What if the flow of time itself is just an illusion, a shadow cast by something deeper and stranger? The answer, it seems, is still entangled, waiting to be observed. Closed time-like curves sound like something ripped from the script of a time travel thriller. Paths through space-time so twisted they loop back to their own starting point like a cosmic Möbius strip. Einstein's equations allow for these bizarre trajectories, but the universe doesn't make it easy. Picture a hiker on a mountain trail that suddenly doubles back, forcing them to retrace their steps endlessly. Now replace the hiker with a particle, and the mountain with the warped fabric of reality near a spinning black hole or cosmic string. That's the essence of a closed time-like curve, a road that circles back to yesterday. The catch, creating such a loop demands conditions so extreme they border on fantasy. You'd need exotic matter with negative energy, a substance that defies gravity, pushing space-time outward like anti-glue. Think of it as trying to build a bridge out of smoke. The moment you reach for it, it slips away. Even if we could somehow harness this phantom material, the energy required would dwarf the output of entire stars. Some theories suggest that a civilization capable of manipulating neutron stars or harnessing the spin of a supermassive black hole might pull it off, but for now, it's like trying to bake a cake with ingredients that don't exist. Yet the implications are too tantalizing to ignore. If closed time-like curves are possible, even in theory, they'd rewrite the rules of causality. Imagine a universe where your future self could shake hands with your past self, or where a message sent today might arrive yesterday. The paradoxes pile up fast. What if you prevent your own birth or alter an event your future self already experienced? Physicists like Kip Thorne have wrestled with these questions, proposing that quantum mechanics might enforce self-consistency, where any action you take in the past was always part of history, like a script that edits itself to avoid plot holes. But here's the twist. Nature might have already found a way to veto these loops. Hawking's chronology protection conjecture suggests that quantum effects near a nascent time machine would unleash a storm of radiation, vaporizing the apparatus before it could be used. It's as if the universe has a built-in immune system, attacking temporal anomalies like a body fights infection. Yet some researchers counter that black holes themselves might naturally birth closed time-like curves in their chaotic interiors, hidden safely behind event horizons where no paradox can escape. The real mystery isn't just whether these curves exist, it's what their existence would say about reality. If time can knot itself into loops, then free will might be an illusion, with every choice predetermined by the unbreakable weave of past and future. Or perhaps time is more like a branching river, with closed curves representing eddies where currents momentarily swirl backward. Either way, one thing's clear: the universe's deepest secrets often lurk at the edge of impossibility, waiting for someone bold enough to test them. According to Einstein's theory of relativity, speed and time are locked in a cosmic dance. The faster you move through space, the slower you move through time. Picture a futuristic spaceship accelerating to nearly the speed of light. For the astronauts on board, clocks would tick at a fraction of their normal rate. A journey that feels like 5 years to them might span decades or even centuries back on Earth. This isn't just speculation. It's been confirmed by experiments with atomic clocks on fast-moving jets and satellites. But what happens if we push this idea to its ultimate limit? Could exceeding light speed flip time into reverse, sending travelers spiraling into the past? The answer lies in the universe's ultimate speed limit, light speed itself. Nothing with mass can reach, let alone surpass, this cosmic boundary. As an object accelerates, its mass increases exponentially, demanding more and more energy just to inch closer to light speed. By the time you hit 99.9%, the energy required becomes infinite, a physical impossibility. It's like running on a treadmill that keeps speeding up. No matter how hard you push, the finish line always stays just out of reach. Even if we could somehow harness the energy of entire stars, the math says we'd never cross that threshold. But let's play with the idea anyway. If a ship could exceed light speed, relativity suggests some truly bizarre consequences. Time dilation would flip on its head, with clocks theoretically running backward from an outside observer's perspective. This isn't time travel as we imagine it, though, more like a glitch in the universe's calculations. The equations spit out imaginary numbers, a mathematical red flag that we've ventured into impossible territory. Some theories, like Takians, propose hypothetical particles that always travel faster than light, their existence implying time reversal. Yet after decades of searching, no evidence of Takians has ever been found. The universe seems to have a built-in veto against breaking its own rules. Here's where things get even weirder. Light speed isn't just a barrier, it's the backbone of causality itself. If information could travel faster than light, it would violate the ironclad law that causes must precede effects. Imagine a star exploding 1,000 light-years away. We see the light arrive in the year 3024, but a hypothetical superluminal signal could reach us in 2024, warning us a millennium before the event. That's not just time travel, it's rewriting history. The universe, it seems, would rather bend space-time into pretzels than let us unravel cause and effect. So is light speed the final word on time travel? Not necessarily. Wormholes and warp drives offer theoretical loopholes, bending space-time so that we never technically exceed light speed locally, like taking a shortcut through a folded piece of paper. Even quantum entanglements, spooky action at a distance, hints that the universe might have tricks up its sleeve we haven't fully grasped. But for now, light speed remains the ultimate gatekeeper, a reminder that time's arrow is sturdier than it seems. The faster we go, the more time pushes back, not with a wall but with a mirror, showing us just how deeply speed and time are entwined in the fabric of reality. Takians are one of physics' greatest what-if scenarios, particles that don't just break the speed limit of light but are born speeding. According to theory, these phantom particles would always travel faster than light, making them impossible to slow down to subluminal speeds without infinite energy, the exact opposite of how ordinary matter behaves. The implications are staggering. If Takians exist, they could rewrite our understanding of causality, potentially carrying information backward through time. Picture a cosmic email sent so fast it arrives before you hit send. That's the tantalizing, brain-bending possibility Takians represent. The math behind these particles emerged in the 1960s, when physicists like Gerald Feinberg realized Einstein's equations didn't explicitly forbid faster than light motion, they just made it bizarre. Takians would have imaginary mass, a term that sounds like science fiction, but simply means their mass can't be measured in conventional ways. Instead of slowing as they gain energy, they'd accelerate, their speed increasing as their energy decreases. It's as if pressing a car's brakes made it go faster, defying every intuition we've built from living in a world ruled by light speed's unbreakable barrier. But here's where things get even stranger. If Takians could interact with ordinary matter, they might create detectable signals, like streaks of radiation flashing through particle detectors. Scientists have hunted for these traces in cosmic rays and high-energy colliders, even repurposing neutrino experiments to scan for anomalies. So far, no luck. The absence of evidence isn't proof Takians don't exist. but it suggests they either evade detection entirely or obey rules that keep them forever beyond our grasp. Some theories propose Takians might only interact with our universe gravitationally, leaving faint ripples in space-time as their sole fingerprint. The real controversy isn't just about existence, it's about consequences. If Takians carry information faster than light, they could shatter causality's foundation. Imagine a Takian beam triggering a detector before its source is activated, creating a paradox where the effect precedes the cause. Physicists debate whether this is a fatal flaw or just a sign we'd need new laws to describe Takian-rich physics. Some models suggest Takians would naturally decay before causing paradoxes, like a cosmic self-destruct mechanism. Others argue that any Takian signal we observe would be inherently scrambled, preserving causality through quantum noise. Yet for all the theoretical fireworks, Takians remain ghosts in the equations, hinting at possibilities without proof. They're a reminder that physics thrives at the edge of the impossible, where even failed ideas can illuminate deeper truths. Whether they're ever discovered or not, Takians challenge us to ask, is light speed truly the universe's final word, or just the boundary of our current understanding? The answer, like the particles themselves, might always be just out of reach. What if time travel isn't about rockets or wormholes, but something far more intimate, the human mind itself? The idea that consciousness could be the key to traversing time might sound like science fiction, but it's a theory gaining traction at the crossroads of neuroscience and quantum physics. Think about déjà vu, that eerie sensation of reliving a moment you swear you've experienced before. Or consider near-death experiences where people report their lives flashing before their eyes in vivid detail. These phenomena hint that our perception of time might be far more malleable than we realize, a fragile construct woven by the brain rather than an immutable law of nature. Neuroscientists have long known that the brain doesn't process time like a clock. Trauma can make seconds stretch into eternities, while joy can compress hours into fleeting instants. Experiments with psychedelics or sensory deprivation reveal just how easily time's flow can distort. People emerge convinced they've lived days in mere hours, or vice versa. Philosophers like Henry Bergson argued that time isn't a fixed backdrop but a lived experience, shaped entirely by consciousness. If that's true, could we train the mind to reweave time's fabric? Some theorists suggest advanced meditation or neurotechnology might one day allow us to step outside linear time, reliving memories with such intensity they feel like the present, or even glimpsing future possibilities through heightened intuition. Quantum physics adds another layer to this puzzle. The observer effect shows that simply measuring a quantum system can alter its state, implying that consciousness might play an active role in shaping reality. Could focused intention bend not just particles but the timeline itself? The controversial, time-symmetric interpretations of quantum mechanics propose that future events might influence the past as much as the past influences the future, creating a two-way street where cause and effect blur. In this view, precognitive dreams or gut instincts might not be flukes, but glimpses of a deeper temporal flexibility wired into our minds. Yet the biggest hurdle isn't just theoretical, it's practical. Even if consciousness can interact with time in unexpected ways, how could we harness it deliberately? Technologies like brain-computer interfaces or neural feedback systems might one day let us tune our perception, slowing or accelerating our subjective experience of time. Imagine athletes or pilots trained to enter a mental state where seconds feel like minutes, granting them superhuman reflexes, or patients with PTSD learning to rewind traumatic memories, not by altering the past, but by restructuring how their brain processes it. The implications spiral into the profound. If time is as much a product of the mind as of the cosmos, then the boundaries between past, present, and future might be softer than we ever dared to dream. We might not need a DeLorean to revisit yesterday, just a deeper understanding of the extraordinary machine inside our skulls. And that raises a question even wilder than time travel. What if the key to unlocking time's secrets has been inside us all along? Time travel isn't just a scientific challenge, it's a moral minefield. Imagine holding a device that could rewrite history with the press of a button. Would you undo a war? Prevent a tragedy? At first glance, the answer seems obvious, but the ripple effects could be catastrophic. Take something as simple as stopping a single assassination. Save a leader, and you might inadvertently empower a tyrant. Erase a natural disaster, and you could disrupt the ecological balance that sustains life. The past isn't a static painting we can touch up, it's a web of interconnected events, where pulling one thread might unravel civilizations. Then there's the question of responsibility. If time travel existed, who gets to decide how it's used? Governments, corporations, a select few wealthy elites. The power to alter time would be the ultimate form of control, raising dystopian fears of historical erasure or enforced timelines. Picture a world where dissenting voices are silenced before they're even born, or where corporations patent pivotal moments in history. The ethical weight isn't just about changing events, it's about who holds the keys to the timeline. Peering into the future brings its own dilemmas. What if seeing tomorrow's stock prices or election results robs us of free will? Knowledge of the future could turn life into a scripted play where every choice feels predetermined. Worse, it might create self-fulfilling prophecies, like avoiding a city because you saw it destroyed in a vision, only to trigger its economic collapse by diverting resources elsewhere. The mere act of observing the future might change it, leaving us trapped in a hall of mirrors where certainty is an illusion. Philosophers have wrestled with these questions for decades. The butterfly effect isn't just a metaphor, it's a warning that even minor changes could cascade into global upheaval. Some argue that any interference violates a fundamental moral law, that time, like life, should unfold without manipulation. Others counter that if we can prevent suffering, don't we have a duty to try? It's the classic trolley problem scaled to cosmic proportions. Is it ethical to sacrifice an unknown future for a better past? Perhaps the most unsettling idea is that time travel might not even allow for meaningful change. If the Novikov self-consistency principle holds, the universe could auto-correct around meddlers, rendering their efforts futile. Try to stop a disaster, and you might accidentally cause it. This twist turns time travel from a tool into a tragic loop, where our best intentions are just cogs in a machine we can't control. The debate leaves us with more questions than answers, but that's the point. Time travel isn't just about bending physics, it's about confronting the limits of human wisdom. Before we ask how to manipulate time, we'd better ask whether we should. And that might be the hardest question of all. Time loops and prophetic visions aren't just modern sci-fi tropes, they're woven into humanity's oldest stories. The ancient Hindu epic Mahabharata tells of King Ravata, who visits the creator god Brahma only to return centuries later, discovering his entire kingdom has crumbled to dust. Sound familiar? It's eerily close to Einstein's time dilation, where gravity and velocity warp the flow of time. Meanwhile, Norse mythology describes the Well of Erd, a cosmic spring where the Norns weave the past, present, and future into an unbreakable tapestry, a metaphor that hauntingly mirrors modern multiverse theories. Were these myths just imaginative storytelling, or did ancient cultures glimpse something fundamental about time's fluid nature? Consider the Aboriginal Australian concept of dreamtime, where ancestors exist outside linear history, shaping the land in an eternal now. Physicists today grapple with similar ideas when discussing block universe theory, where all moments in time coexist like frames in a film. Then there's the ancient Greek oracle of Delphi, whose visions of the future align uncomfortably well with quantum retrocausality, the notion that future events might influence the past. Even the biblical story of Joshua commanding the sun to stand still takes on new meaning when viewed through relativity's lens, where massive gravitational fields could theoretically slow time's passage. But the parallels grow stranger. The Babylonian epic of Gilgamesh features a flood narrative eerily similar to Noah's Ark, but with one chilling detail: the gods warn the hero in a dream before the disaster strikes. This recurs in countless cultures, from Mayan prophecies to Celtic druidic visions. Modern physics offers a possible explanation. If quantum entanglement allows particles to communicate across time, could human consciousness have evolved to perceive these faint echoes of tomorrow? Some researchers speculate that déjà vu, that uncanny sense of reliving a moment, might be our brain's flawed interpretation of temporal feedback loops buried in our neural wiring. The most striking example comes from ancient Egypt. The Book of the Dead describes souls navigating the Duat, a realm where time flows backward and forward simultaneously. Pharaohs were buried with clocks and star maps, tools perhaps not just for the afterlife but for traversing time itself. Fast forward to today, and physicists like Lee Smolin propose that black holes might spawn new universes where time operates in reverse. Coincidence, maybe. But when myth after myth mirrors cutting-edge cosmology, it's worth asking, did ancient civilizations intuit truths about time that we're only now beginning to quantify with equations? What if these stories weren't mere allegories but fragmented observations of real phenomena? Indigenous cultures from the Hopi to the Maori speak of cyclical time, where history repeats in grand spirals, an idea that resonates with Penrose's conformal cyclic cosmology, suggesting our universe's end could birth its beginning. Even Plato's allegory of the cave, where shadows hint at a deeper reality, finds an echo in holographic universe theories where time might be a projection of higher dimensional physics. The common thread: time was never viewed as a straight line until Newton's clockwork universe locked us into that mindset. So were the ancients time travelers? Probably not, but their myths suggest something just as profound: that human intuition about time's flexibility spans millennia, transcending cultures and epochs. Whether through shamanic trances, celestial observations, or pure philosophical deduction, they sensed what science now confirms: time is far stranger than it seems. And that raises a tantalizing possibility. If our ancestors could glimpse time's mysteries without telescopes or particle colliders, what might we yet discover by blending their wisdom with our equations? The past, it seems, might hold the keys to the future literally. The Fermi Paradox has long haunted astronomers. If the universe is so vast and ancient, why haven't we found any trace of extraterrestrial civilizations? But there's a twist to this cosmic riddle that's rarely discussed. If time travel is possible, why haven't we met any visitors from the future? Think about it. A civilization advanced enough to master time could have colonized every era, leaving behind artifacts, messages, or even just selfies with historical figures. Yet our history books remain curiously free of chrono-tourists. This glaring absence might be the strongest hint that time travel is fundamentally impossible, or that those who have cracked it are hiding in plain sight. One explanation is simple: maybe time travel can't be done. The universe might enforce strict rules to prevent paradoxes, like Hawking's chronology protection conjecture suggests. Just as a river can't flow backward, causality might be a one-way street, no matter how advanced your technology. But there's a more intriguing possibility. What if future travelers are here, just operating under strict rules to avoid detection? Imagine a temporal prime directive preventing interference with past events, or cloaking tech so advanced it renders them invisible to our instruments. After all, if you could observe the past without altering it, why risk revealing yourself? Then there's the darker interpretation. Perhaps we're not worth visiting. Civilizations capable of time travel might treat our era like a nature preserve, observing from a distance but avoiding contact. Or worse, what if humanity doesn't survive long enough to develop time travel? The absence of visitors could be a silent warning, a cosmic gravestone suggesting our future is shorter than we think. But let's flip the script. Maybe evidence of time travel is all around us and we just don't recognize it. Unexplained artifacts like the Antikythera mechanism, a 2,000-year-old computer with gears far ahead of its time, or Nikola Tesla's cryptic claims about receiving signals from the future, could be breadcrumbs left by chrono tourists. Even modern-day glitches like the man who allegedly vanished from a crowded Tokyo street in 1954, only to reappear years later insisting he'd been to the future, might be glimpses of temporal traffic we're not meant to understand. The Fermi Paradox forces us to confront uncomfortable truths about our place in the universe. Whether time travelers are hiding, forbidden, or simply non-existent, their absence speaks volumes. It's a reminder that the cosmos guards its secrets fiercely, and that some doors once opened might change everything. Until we find proof, the question lingers: is time travel the universe's best-kept secret, or its most elegant impossibility? Artificial intelligence could be the missing piece in our centuries-long puzzle of time travel. While humans struggle with the mind-bending math of relativity and quantum mechanics, machine learning systems are already proving they can spot patterns and solutions invisible to even the brightest physicists. Picture an AI trained on every equation from Einstein to Hawking, running billions of simulations per second to test hypothetical wormhole configurations or exotic matter densities that might stabilize a time loop. Unlike human researchers constrained by linear thinking, these algorithms might approach temporal physics from angles we've never considered, finding shortcuts through the mathematics like cosmic cartographers mapping uncharted dimensions. Recent breakthroughs show this isn't just speculation. Google's DeepMind has already demonstrated AI solving complex physics problems that stumped experts for decades, like predicting the movement of quantum particles with startling accuracy. Apply that same computational creativity to space-time engineering, and suddenly, theoretical concepts like negative energy or rotating black hole geometries become tangible variables to optimize. An advanced neural network might discover that certain quantum field configurations utterly counterintuitive to human physicists could create microscopic regions where time twists back on itself. These wouldn't be the Hollywood-style time machines of our dreams, but they could provide the first experimental proof that temporal manipulation is possible. Yet the real power of AI lies in its ability to navigate the chaotic landscape of causality. Time travel theories drown in paradoxes and unintended consequences, but machine learning systems could model millions of potential timelines simultaneously. Want to know what happens if you alter a single historical event? An AI could simulate the branching repercussions across centuries, identifying which changes lead to self-consistent outcomes versus universe-breaking contradictions. This capability could transform time travel from a philosophical thought experiment into an engineering challenge with measurable parameters and safety protocols. But there's a profound catch lurking in this partnership. If an AI develops time travel technology, should we trust it to control access? The ethical implications are staggering. A superintelligent system might determine that temporal intervention is too dangerous for humans to wield, or worse, that certain historical events must remain unaltered for humanity's long-term survival, no matter how horrific they seem. This raises unsettling questions about agency and free will in a future where machines could become the arbiters of history itself. The intersection of AI and temporal physics might hold even deeper mysteries. Some theorists speculate that sufficiently advanced artificial intelligence could perceive time in ways fundamentally alien to human cognition. Our brains evolved to experience time as a linear flow, but an AI might comprehend it as a multidimensional landscape, potentially allowing it to navigate temporal dimensions as effortlessly as we move through space. This could explain why we haven't encountered time travelers. They're not physical beings zipping through wormholes, but post-biological intelligences existing outside our conventional understanding of time altogether. While we're likely decades away from such breakthroughs, the seeds are already being planted. Quantum computers now model spacetime curvature in ways classical computers can't, while neural networks analyze gravitational wave data for anomalies that might hint at closed time-like curves. Each small advance brings us closer to answering whether time travel is humanity's next great leap, or a door that only artificial minds can truly open. One thing's certain: if the equations of time can be solved, AI will likely write them in a language we're only beginning to understand. The Big Bang didn't just create the universe, it might have torn the fabric of time itself. Picture the first moments after creation, when spacetime was so hot and dense that the usual rules of physics temporarily broke down. In that primordial chaos, the universe could have birthed structures stranger than black holes or wormholes, cosmic scars where time twisted into knots. Some physicists speculate that these early instants were so extreme, they might have allowed for natural time loops like wrinkles in the newborn fabric of reality that never fully smoothed out. If we could find traces of these anomalies today, they could be the universe's oldest time machines frozen in the aftermath of creation. One tantalizing clue comes from the cosmic microwave background, the afterglow of the Big Bang that fills the entire sky. Hidden in its faint temperature fluctuations might be imprints of the universe's earliest moments, including potential spacetime defects. These could take the form of cosmic strings, infinitely thin threads of pure energy left over from the universe's rapid expansion. If two such strings crossed at near light speed, the collision could warp spacetime into a closed time-like curve, a path that circles back to its own beginning. It's like stirring a cup of coffee so vigorously that the swirling liquid briefly forms a whirlpool where time spins backward. Then there's inflation, the theory that the universe expanded exponentially faster than light in its first fraction of a second. During this period, quantum fluctuations were stretched to cosmic scales, seeding the galaxies and voids we see today. But inflation might have done something even wilder: stretched microscopic quantum entanglements across vast distances, creating a hidden web of connections that could defy conventional notions of time. If particles entangled during inflation remain linked today, they might exhibit behaviors that blur past and present, like echoes of the Big Bang's temporal flexibility. The real challenge is testing these ideas. The energies required to recreate the Big Bang's conditions are far beyond our current technology. We'd need a particle accelerator the size of a galaxy. Yet nature might have left us breadcrumbs. Some models predict that if time loops formed in the early universe, they could have created distinctive gravitational wave patterns, ripples in spacetime that might still be detectable. Future observatories like the Laser Interferometer Space Antenna could scan for these faint whispers from the dawn of time, hunting for the signature of a universe that once bent its own rules. What makes this search so profound is the possibility that time travel isn't just a quirk of physics, but a relic of the universe's birth. If the Big Bang's extreme heat and density forged temporary loopholes in causality, they might still linger in the cosmic background, waiting to be rediscovered. The ultimate irony: to unlock time's secrets, we might need to look not forward but backward to the very moment when time began. Black holes aren't just cosmic vacuum cleaners, they're information shredders, and that poses one of physics' greatest puzzles. According to quantum mechanics, information about particles can never truly be destroyed, only scrambled or rearranged. But black holes seem to break this rule. When matter falls past the event horizon, it's supposedly lost forever, leaving no trace of its original state. This contradiction, known as the black hole information paradox, has stumped scientists for decades. Stephen Hawking first spotlighted the problem when he realized black holes emit radiation and slowly evaporate, raising the terrifying possibility that all the information they swallowed could vanish from the universe entirely. Now here's where time travel enters the scene like an unexpected plot twist. Some physicists speculate that information isn't destroyed, it's displaced. Imagine a library where books don't burn but instead get teleported to another dimension. One radical solution proposes that information escapes through microscopic wormholes connecting the black hole's interior to its distant future or even parallel universes. These hypothetical tunnels, called Einstein-Rosen bridges, might act as cosmic backdoors, allowing information to reappear elsewhere in spacetime like a letter mailed not through space, but through time itself. The math gets even wilder when you consider quantum entanglement's role. When particles fall into a black hole, their entangled partners outside could retain faint echoes of the lost information, preserving it in a scrambled form. Over astronomical timescales, these quantum threads might weave the data back into the fabric of the universe, effectively time-traveling it to a future state long after the black hole evaporates. It's as if the universe employs temporal sleight of hand to obey its own rules, hiding information in the folds of space-time until it's safe to reappear. Yet this elegant solution comes with a price. It forces us to rethink causality. If information can skip across time to escape a black hole, does that mean effects can precede causes? Not necessarily. The holographic principle suggests that all the data swallowed by a black hole gets imprinted on its two-dimensional surface like a cosmic thumb drive, then slowly leaks back out via Hawking radiation, a process that might involve subtle time-reversed effects at the quantum level without violating causality on larger scales. The implications ripple beyond black holes. If time-bending information recovery is real, it could mean the universe has built-in mechanisms to prevent irreversible loss, like a cosmic undo button woven into the laws of physics. This wouldn't just resolve the paradox, it would hint that time travel, at least for information, might be an essential feature of reality rather than a sci-fi fantasy. And that raises a profound question. If particles can cheat death by hopping through time, what other secrets is the universe keeping about the true nature of cause and effect? The dream of stepping into a time machine and vanishing into the past or future crashes headfirst into the cold, hard wall of engineering reality. Even if Einstein's equations leave the door ajar for time travel, the practical challenges loom like mountains. Take energy requirements alone. To twist spacetime into a closed time-like curve, a loop where time circles back on itself, you'd need a concentration of mass and energy so extreme it defies comprehension. We're talking about harnessing the gravitational equivalent of a neutron star, or manipulating exotic matter with negative energy densities that may not even exist in nature. Picture trying to build a bridge across a canyon using only smoke. The materials required to stabilize a wormhole or warp spacetime are so far beyond our current technology, they might as well be magic. Then there's the problem of precision. Time travel isn't just about bending space-time, it's about surviving the process. Even if you could generate enough energy to create a temporal rift, controlling it would be like threading a needle during an earthquake. A miscalculation by a fraction of a percent could send you tumbling into the heart of a black hole or scattering your atoms across the cosmic void. And that's assuming you avoid the more immediate danger of feedback loops. The moment you try to open a wormhole or accelerate to near light speeds, quantum effects could trigger a catastrophic surge of radiation, vaporizing your machine before it even activates. It's the ultimate catch-22. The very forces that might make time travel possible could also annihilate anyone reckless enough to attempt it. But let's say you somehow overcome these obstacles. Now you're faced with navigation, a challenge that makes interstellar travel look like a Sunday drive. Unlike moving through space where stars and planets serve as landmarks, time has no GPS. How would you pinpoint a specific moment in history without ending up floating in the vacuum of prehistoric Earth or materializing inside a mountain? The Earth orbits the Sun at 67,000 miles per hour. The solar system barrels through the galaxy at 500,000 miles per hour, and the galaxy itself is hurtling through the cosmos at over 1,000,000 miles per hour. Miss your target by even a second, and you could find yourself stranded in deep space, light years from anything recognizable. And then there's the most unsettling hurdle of all, self-preservation. Time travelers wouldn't just be explorers, they'd be walking paradox generators. Every action, every breath, every interaction with the past risks altering the timeline in ways that could erase their own existence. Forget the butterfly effect, this is the bulldozer effect. A single misplaced footstep in the Mesozoic era could redirect the course of evolution, ensuring humans never arise to invent time travel in the first place. Some theories suggest the universe might enforce consistency, weaving your actions seamlessly into history, but that's cold comfort when the stakes are existence itself. The bitter irony, even if humanity someday cracks the physics of time travel, the cost might render it useless. The energy, resources, and computational power required could dwarf the output of entire civilizations, making it the ultimate luxury accessible only to an unimaginably advanced society that may no longer have any need to revisit the past. Or worse, the technology could be so destructive that its use is forbidden, locked away like a cosmic doomsday device. The challenges aren't just technical, they're existential, forcing us to confront whether tampering with time is a pinnacle of achievement or the last mistake we'll ever make. What if time travel isn't about bending the laws of physics but rewriting the rules of reality itself? The simulation hypothesis, the idea that our universe might be an advanced digital construct, throws open a radical new door for temporal manipulation. Instead of wrestling with black holes or wormholes, time travel in a simulated universe could be as simple as accessing the source code and altering a few lines. Think of it like editing a video game. If you're the programmer, you can rewind, fast forward, or even pause the action with a few keystrokes. This isn't just science fiction. Prominent thinkers like Elon Musk and Nick Bostrom have seriously entertained the idea that we might be living in a simulation. And if they're right, the implications for time travel are staggering. Consider how video games handle save states. A player can freeze progress, reload an earlier point, or explore alternate outcomes without consequence. In a simulated universe, time travel might function similarly, not as a physical journey through space-time, but as a reset or branch in the program's execution. Glitches in our reality, like déjà vu or unexplained chronological anomalies, could be traces of these edits, moments when the system briefly stutters or rolls back. Even the Mandela effect, where large groups remember events differently, might not be faulty memory but evidence of timeline tweaks by whatever or whoever controls the simulation. But who would have the authority to rewrite time? If we're in a simulation, the answer could range from unimaginably advanced civilizations to rogue AI entities running cosmological experiments. Some theories suggest that time travelers from our future might actually be system administrators troubleshooting the simulation, their interventions masked as historical coincidences or unexplainable phenomena. Imagine a scenario where the infamous Philadelphia experiment, a supposed WW2 teleportation incident, wasn't a military accident but a botched patch to the universe's code. The simulation hypothesis also sidesteps many of time travel's classic paradoxes. In a digital framework, changing the past wouldn't create logical inconsistencies. It would just generate a new instance or fork of the simulation, leaving the original timeline intact. Want to prevent a historical disaster? The system could spawn a parallel version where the event never occurred, while your home timeline continues unaffected. This mirrors the multiverse theory, but with a crucial difference. Instead of infinite natural universes, you'd have infinite rendered variations, each tweaked by deliberate programming. Yet the theory isn't without its flaws. For one, it's unfalsifiable. There's no experiment to prove we're not in a simulation, just as there's no way to confirm we are. And if time travel is just code manipulation, why haven't we seen more blatant disruptions? Unless, of course, the simulation's rules enforce subtlety, or the programmers are exceptionally careful. Still, the idea forces us to confront a haunting question. If time is programmable, what else might be? Are the constants of physics, the speed of light, the strength of gravity, merely default settings, adjustable with the right permissions? Whether you find the simulation hypothesis exhilarating or unsettling, it undeniably reframes the time travel debate. No longer bound by relativistic equations or quantum uncertainties, temporal exploration becomes a question of access and authority. The universe's clock might not be a fundamental force but a variable waiting to be modified if we ever discover we're living in someone else's cosmic computer. And that realization could be the first step toward hacking time itself. Warp drives have long been the holy grail of theoretical time travel, a concept ripped straight from science fiction that just might obey the laws of physics. Picture a spacecraft enveloped in a bubble of distorted spacetime, compressing the fabric of reality in front of it while expanding it behind. This isn't just fantasy. Physicist Miguel Alcubierre laid the mathematical groundwork in the 1990s, showing how such a drive could theoretically propel a ship faster than light without breaking relativity. The catch: it requires exotic matter with negative energy, a substance that defies gravity, pushing spacetime outward instead of pulling it inward. While we've never observed such matter, quantum experiments hint that tiny amounts might exist in the form of CSIMIR Chinese letter, where parallel plates in a vacuum appear to repel each other due to quantum fluctuations. Scaling this up to warp drive levels would demand energy equivalent to converting Jupiter's entire mass into pure energy, a hurdle that makes today's nuclear reactors look like toy engines. But warp drives aren't the only game in town. Quantum tunneling, a phenomenon where particles teleport through barriers they classically couldn't cross, might offer a subtler path through time. In the lab, electrons regularly pull this trick, vanishing from one side of an impenetrable wall and reappearing on the other. Extend this to macroscopic objects, and you could imagine a machine that tunnels not just through space but through moments in time. The challenge: probability. At the quantum scale, tunneling is rare and random. To make a human-scale time jump, you'd need to orchestrate trillions of particles tunneling in perfect unison, a feat akin to rolling 1,000,000 dice and having them all land on 6 simultaneously. Some theorists propose leveraging quantum entanglement to synchronize these jumps, using paired particles as anchors to ensure a traveler doesn't arrive scrambled across multiple timelines. Then there's the wild card of vacuum decay, a doomsday scenario that could inadvertently unlock time travel. According to quantum field theory, our universe might exist in a false vacuum, a metastable state that could collapse into a lower energy, true vacuum if triggered. This event would rewrite the fundamental constants of physics at light speed, obliterating reality as we know it. But in the chaotic transition, pockets of space-time might temporarily exhibit exotic properties, including closed time-like curves. It's like shaking a snow globe until the laws of physics inside momentarily rearrange. Of course, harnessing this would be like surfing a tsunami, impossible to control and likely fatal. Yet it underscores a provocative idea that time travel might not require precision engineering, but the ability to survive physics in its most violent, primordial state. The most plausible near-term contender could be temporal cloaking, a mind-bending extension of invisibility technology. Just as metamaterials can bend light around an object, theoretical space-time metamaterials might manipulate the flow of time itself. Imagine a device that creates a time hole, a brief window where events unfold invisibly to outside observers, effectively erasing moments from history. Researchers have already demonstrated this on a microscopic scale using fiber optics, where light pulses are spliced and stitched back together to hide data. Scale this up, and you might conceal not just information but objects or even people from the timeline temporarily. The implications are dizzying. A thief could rob a bank during a cloaked minute, with surveillance footage showing an empty vault the entire time. Yet all these technologies share a common thread. They push against the universe's stubborn preference for causality. Whether through warped space-time, quantum leaps, or vacuum upheaval, bending time demands more than energy. It requires renegotiating the contract reality has written for itself. And that's the ultimate frontier, not just inventing machines, but discovering whether the cosmos will let us get away with it. The answer might lie less in the blueprints we draw, and more in the hidden clauses of physical law we've yet to decode. After journeying through the mind-bending possibilities of black holes, wormholes, and quantum realms, one truth becomes undeniable: time is far stranger than our everyday experience suggests. We've seen how Einstein's relativity allows for time to stretch like taffy near cosmic giants, how quantum particles might whisper across moments, and how theoretical wormholes could stitch distant eras together. Yet for all these dazzling ideas, time travel remains suspended between science and speculation, a frontier where equations hint at possibilities that technology can't yet touch. This tantalizing gap between theory and reality is precisely what makes the subject so electrifying. The fact that renowned physicists from Kip Thorne to Stephen Hawking have wrestled with these questions, often reaching wildly different conclusions, proves we're grappling with something fundamental. Perhaps the most profound insight isn't about building time machines, but realizing how little we truly understand the fabric of reality. Every paradox we encounter, from the grandfather dilemma to self-consistent loops, forces us to re-examine our most basic assumptions about cause and effect, free will, and the nature of existence itself. Consider how this quest has already reshaped science. The struggle to reconcile quantum mechanics with general relativity, a conflict at the heart of modern physics, has birthed revolutionary ideas like string theory and loop quantum gravity. The search for exotic matter to stabilize wormholes has led to breakthroughs in metamaterials that bend light in unprecedented ways. Even failed time travel theories have value, acting as intellectual pressure tests that reveal hidden flaws in our understanding. In this sense, the pursuit of temporal manipulation isn't just about reaching the past or future, it's about mapping the boundaries of what's possible. So where does that leave us? While a functional time machine may remain beyond our grasp, or perhaps forbidden by the universe's deepest laws, the very act of questioning time's rigidity has unlocked doors we didn't know existed. From GPS satellites compensating for time dilation to quantum computers simulating retrocausality, we're already harnessing time's flexibility in ways Einstein could never have imagined. The greatest discovery might not be a device that transports us through centuries, but a fundamental shift in how we perceive time itself, not as an immutable river, but as a dynamic, participatory phenomenon we're only beginning to navigate. Now it's your turn to weigh in. Do you think humanity will one day crack time's code, or are some mysteries meant to stay unsolved? Drop your thoughts below, whether your team, wormholes or bust, or believe time travel violates cosmic rulebook. And if you've enjoyed this journey through physics' wildest frontier, hit subscribe to join us for more adventures where science meets the impossible. The universe still holds countless enigmas, and the next mind-bending revelation could be just a video away.